Okay, so yeah, we have two very interesting talks in the afternoon. So the first one is by Chen Chen, who is at the University of Sheffield, and he's going to be talking about the value of single modality for healthcare through learning from multi-modal knowledge. Yeah. Okay. Yeah. Okay. Okay, thank you.
Okay, thank you. So it's a very great honor to be here to present our recent works about how we can maximize the value of single modality by exploiting multimodal data. So before I start, I would like to give a brief introduction about myself. I'm Chen, and currently a lecturer in computer vision in the School of Computer Science at the University of Sheffield. And I'm also the ELLIS Scholar in Robust Machine Learning program. And also we are holding the honorary research fellow at Imperial College London, where I did both my master's degree and PhD degree there. I'm fortunate to have like a mixed working experience in both academia as well as industry, where I can have the chance to translate what I have developed during my master as well as during my PhD study to the real products, where I get chance to talk to clinicians, understand their problems, and see how AI can help them. So far, I've been working on AI for healthcare for roughly 9 years now. Majority of the time are working on like generative AI or robust or adversarial machine learning, trying to improve the robustness of AI products or models. And recently, we trying to explore multimodal AI and see how it can advance the field. So to start with, I would like to take a small quiz. So I'm sure we are living in a world that there are lots of data generated every day. So I'd like to ask a single question. Do you know how many medical images are generated each year globally? Can you guess? 2 billion. Okay. Any? 10 billion. 10 billion. Okay. Good. So I think the figure is roughly very close to the ground truth. Nowadays it's around 6 billion. Okay, that's about 3.6 billion X-ray images, 1.5 billion ultrasound images because they're low cost and they are often used as a first-line image modality, as well as other CT, ECG, as well as MRI. So this number you may not feel very surprising because, as you know, currently there are like over 8 billion people in the world. Okay, so that's about like everyone will just contribute 1 image per year. Okay, not so fancy. However, let me ask another question. Do you know how many radiologists per million people? Okay, that's okay. But I want to understand the distribution. So how many people think this is A? Raise your hand. Okay, no one. And B? Okay, we got some people. And C? Okay, so I think the majority of them vote for C. And how many people do you think this is D? Oh, we got the fewest people. Okay. But the answer belongs to the minority, unfortunately. So this figure also, I feel very surprised when I check it online, okay? So only 45 per million. If you put these two numbers together, I think this fact is really worrying, okay? So we got 6 million images produced every day, but we only have 45 radiologists per million people to read and interpret them, okay? So you can imagine how heavy is the workload of each radiologist, okay? And this ratio is even lower in low and middle income countries, okay? But even in the United States, the medical error is reported as the third killer in the world, which is quite surprising, right? The first one is the cardiovascular disease, the heart disease, which is my majority of my time spending on how using AI to better do some early diagnosis of CVD. But you can see that there is an urgent need about trying to reduce the workload of the radiologists so that they can spend more time on the clinicians. to provide personalized care. So I think with AI, things can be different. So for example, AI can be exploited in multiple different stages of our medical imaging, the whole pipeline, starting from acquisition, reconstruction, analysis, and diagnosis, as well as treatment planning. According to a report produced by McKinsey, it has been found that roughly 70% of the time of clinicians can be reduced with AI. So this figure is really promising, right? Okay. So another figure is about the, there is kind of like, because of that, there is a emerging and increasing demand about adopting AI in medical image market. So in 2023, the market size is just below 1 billion, okay? And now it's doubled. By 2034, sorry, this will be the speed will be accelerated and reaching to more than 26 billion USD dollars. So that's really amazing. But however, there is always however behind these promising figures, which is, so if you check online, you will find that those AI products, even produced by large companies such as Google, they didn't really perform quite good on the real world data, okay? And that is 2020. So in 2021, which is kind of like a late stage of the COVID, so there are lots of like hundreds of AI products have been developed to tackling, to detect COVID, okay? But none of them helped, which is really astonishing. And this is the latest one I checked last year in 2024, and from Nature, that they found that the medical AI still fails to assess the patients when they never seen during the training, okay? So the problem behind it, one of the major problem behind it is so-called like the domain shift problem, okay? So imagine you want to train a classifier trying to detect the breakfast, which is what I ate this morning, the traditional British breakfast, okay? And trying to detect some or classify some images that you collected from different regions, such as the one in Hong Kong, which is some noodles, and some, this is some breakfast, a traditional breakfast in Morocco. So the classifier will fail to simply treat it as maybe this is not a breakfast, okay? That's very simple. So in the medical world, things are quite similar. So maybe you got some images like this. Okay, same, this is the, but at real world, you may got image like this. So they are from the same patient, but the undergo image synchronous are different because they're using different protocols and contrast, okay? So this is the contrast enhanced images, where a contrast agent will be injected into the blood, and then the infected regions will be highlighted. And in another scenarios, you may have some like artifacted images, such as there is like a bright regions across these images, and such subtle changes in the intensity distributions can for the neural network to make a different decision, okay? So how to solve, why there is a problem? So all these AI models can, as we know, most of them are like a data-driven approaches, which can be summarized into a simple diagram between data and the model, okay? So we're trying to get some training data, and we're trying to minimize it by optimizing the underlying parameters of the neural network, for example, in a way so that the performance on the downstream test data can be reached to some satisfying performance. And the reason why it works is that we assume that the training data are coming from the same distribution, okay? However, in reality, that assumption does not hold, actually. So there are multiple different reasons, especially in medical domain. So one is because labeling medical images require expertise. So it's not like you can just ask random people to label it. So you need to find someone who has the expertise to label the data, which is even more time consuming, as well as cost, it requires high costs. So people are thinking whether we could just collect lots of data from different existing resources and combine them into a very large data set, okay? The thing is that different clinical centers or different radiologists, they may share different opinions. There is some like label inconsistent problem. And also sharing data, or especially medical data, can be quite sensitive because it involves some protected attributes in the data set. And there are some concerns regarding the security as well as the privacy issues, okay? So how can we solve this? So we have done lots of work in the first solution, which is quite simple, where we're trying to do some data generation or data augmentation. We are trying to synthesize new domains. The easiest one would be the standard that I think everyone will do, is just do some random data augmentation transformations. But we can do it even smartly by utilizing the recent state of that generative networks, such as diffusion models. I'm sure you have like a tutorial yesterday about it. And you can also using GANs or VAEs to do some interpolations in the latent code, and then you can generate some new data. Most recently, we're working on how we can generate the better by trying to generate the worst case scenario, okay? Trying to explore the boundary of the data, trying to improve the robust feature learning by exposing the model with hard examples. And this involves adversarial approaches or causality-inspired approaches. That's why the one we're trying to incorporate some domain knowledges by incorporating some physics priors or some medical knowledge, clinical knowledges into the generation of the data. But today I'm going to talk about another different approach, which is orthogonal to this approach, which is trying to leverage massive unlabeled data, multi-modality data, to learn some transferable representations, okay? And so today's talk will be divided into two parts. The first part is about multi-view data. So I also think this is kind of like multi-modality data. The second part will be covering multi-type data, or this is a more general conception that people think this is multi-modality, where you got some text data, like medical reports, or some signal data, and trying to improve the representation for the other modality, okay? So let's talk about the first part, which is the multi-view data. So this is a work we presented in last year's MICAI, which we got the oral presentation, which is beyond the single 2D images. So I need to give you some background, because in case someone is not familiar with about the cardiac MR imaging. So normally, when you go to the hospital, the clinicians will, the radiologist will give you like a MR scan, which is the ground truth or the golden standard about how people are assessing your heart conditions, okay? That involves actually lots of multi-view 2D plus T series. And one important step is trying to extract the cardiac shape from it. And to do it, people will develop like a neural networks, for example, to help the clinician to automate the process. And usually this is done, like, for example, we have like, in this case, we have 3 different views. You just train a different neural networks on each different views, okay? So in this work, we're trying to answer whether we can train a single unified model that can handle different views and trying to make it versatile to a wide range of clinical tasks, okay? So the idea is quite simple, where we're trying to do some self-supervised learning on unlabeled multi-view data. And that doesn't require any labeling from the radiologists or the clinicians. So this is quite cheap. And we can exploit in large-scale data. And after that, we can do some fine-tuning on the small, limited labeled data, but high-quality data to fine-tune for different tasks. So a brief, because I'm not sure whether, because this is summer school, so I think I might need to cover some basics about self-supervised learning, which is kind of like a current one of the methods trying to learn some useful representations through some pre-text task that does not require manual labeling. And there are like 2 main streams of doing this. One is contrastive learning. And here, this is kind of like Sinclair, where you just do some data augmentations and you treat the augmented data as positive pairs, whereas data from different subjects are considered as negative pairs. So you're trying to push the positive pairs to be close to each other, while trying to dispart these negative pairs to be as far as away from each other. And the second part is about doing some masked recovery, where you just gently mask some patches of the images and you ask the neural network to recover it. By doing so, you can allow the network to exploit the internal relationship behind it. Okay, so we adopt the second approach where we're trying to do some masked modeling about the multi-view data, where we randomly mask patches along the spatial domain as well as the temporal domain. And in this way, we can learn some representations that can be generalizable to various different tasks. Okay, and there is some nice properties. So for example, this can enable us to achieve higher data efficiency. So for the downstream task, we only require a very small limited label data to fine tune it. And the second is about the robustness, because at the pre-training, we randomly mask some of the patches. So even at the test time, if there is like a single view is not available, we can still perform some inference, okay? And last is we found that it can achieve higher accuracy because at the, for example, at the segmentation, we can just expose the model with all the different multi-views, and then it can segment the subjects based on not only its own views information, but as well as the other views information. So for example, this is one of the visualization about segmentation result we get. And here is kind of like the method that we're trying to take the multi-view input as the input to our segmenter, and this gives us a better accuracy compared to those who only just focusing on the information given in a particular view, okay? So let's review about the first work. We're trying to exploiting cheap unlabeled data to via self-supervised learning to learn some generalizable, transferable representations, okay? So in this way, we get some like a knowledge, which can be like a cross-view information or the complementary shape information across different views to enhance the segmentation on the other views, and it can also be used for other tasks, okay? So at the second stage, which is very standard, that is task-specific fine-tuning. So what happened if we even don't have unlabeled data or resource for pre-training, which is quite common in academia, right? So there is a second approach or third approach we propose that is trying to leverage existing foundation model in the world. Okay, so that is already pre-trained by other research groups or other companies and directly use it and trying to fine-tune our model. And this is and we can do some internal multimodal learning in the second stage, okay? So this is the work that we just got accepted in the MICAI 2025, which is focusing on our task called the drag response prediction. So the problem setting is that we're trying to predict the drug response for the neuropathic pain and to see whether it is effective or not. And the input is the resting state fMRI, okay? The output is we just simply treat it as a classified. 0 means this is not effective, 1 means it is effective. So what we do, the problem we are facing that we only have very limited this pain data set, very limited. So if we directly train a neural network, it will be easily to get overfitted. Okay. So what we do in this work is that we're trying to leverage existing foundation model. So here we use in BrainLM, which was pre-trained on a large scale, not specifically for pain study, but for other study, but they are all like resting state fMRI data. And what they do is simply just also the mask modeling method to learn some representations. And we're taking that pre-trained encoder in this work. And the second contribution we do is that, so here, so previously the BrainLM is basically used for the trying to exploiting the information from the time series, which is derived from the fMRI. So in fMRI, you got some different brain regions. I'm sure Emma will give out more details about this in the second talk. But the idea is that you're working on some time series where each line here tells you the brain activities for each region of your brain. And this is the input required by the BrainLM. So we do one step further. what we do is trying to exploiting the correlation between different brain part activity. So it's kind of like a secondary attribute of this data. And we concatenate all this information together and trying to fit it into a classifier. And this is the result. And we found that leveraging foundation models can help us to generalize pattern on different data. Okay, so we achieved the sorter method on both in-house dataset as well as the public datasets. And you will also find that our method, which leverage both modality, which here is the functional connectivity as well as the time series, outperform those who only leverage one modality. Okay. And it is very interesting. We found that when we look into different data sets, there are different patterns of the attribution for each modality. Whereas in the open neural data set, we found that the model prefer to attribute high importance to the time series data, whereas in our in-house data set, it will attribute more to the functional connectivity data. So this is a very interesting finding, and which also reveals importance of doing multimodality, where you give some flexibility for the model to choose the right property of the data. Okay, so that's the first part. The second part is about multi-type, which is our most general concept about multimodal learning, where we're trying to leverage existing data in the hospital. So normally, one of the most valuable resources is medical reports, which is already in the PACS systems. So we think, why not we just utilize those medical reports to learn some scalable representation. Okay. So for example, for each X-ray images, or for example, for each ECG images, we will get some report like this, which give you some valuable information, so not only just about the pathology, it will also give you some information about some clinical knowledge, or even this is healthy, it will give you like there's no specific finding. So this can be a very valuable resources to help us pre-train. So this is the sport solution that we're trying to solve this problem, where we're trying to leverage some data with reports. And in order to extract some useful information from the report, we use LLM, the large language model, to get some representation. And then we can do some LLM informed pre-training, which is trying to align the representation from the report to guide the representation learning on the other modality, where in some cases it can be images, in other cases it can be signals or different modality. And in the second stage, we can just do task-specific fine-tuning where the report may not be necessarily available. Okay. But there are three challenges that I summarized when we're trying to do LLM informed pre-training. The first one is there may be some presentation collapse. So there is like I was saying that a good picture is worth of more than 1,000 of words, right? And the report can be just like 10 words, 20 words. And if we simply align, for example, the medical images to the representation of the report, it may miss other important information. So that's the first challenge. The others are misalignment and some complexity and ambiguity in the medical report, which I will give a more explanation in the further slides. So let's talk about the first challenge, that is addressing the modal collapse problem. Okay, so this is the work we also presented at the MICAT 2023, one of the earliest work for the vision language model pre-training. And the task overview is like this. So this is one general paradigm when we're trying to use X-ray as input and trying to produce train a neural network to produce different tasks, whether to classify whether this is abnormal images or normal images, or trying to detect whether there is some abnormal regions or pneumonias in certain regions of the lungs. So before we're doing that, in this work, we're trying to first align to medical reports. And there's nothing fancy about it. What we do is just do some mean squared error to minimize the difference between the two, okay? But what we're trying to introduce is so-called the orthogonal laws, which trying to encourage the elements in the latent space to be different to each other. Okay, so trying to encourage that it's kind of like a lightweight PCA, where you're trying to encourage the orthogonality in the latent space, so that when we're trying to visualize the latent space, as you can see, that M flag gives you a much well-spanned latent distribution, okay, which can be a good signal to indicate it's a strong generalizable performance on a wide range of different tasks. And so we tested it on different data sets. So we pre-trained the model on multiple different data sets. So we're using 220K from the MIMIC dataset, which is currently one of the most popular multimodal modalities for medical domain. And then we fine-tune it on different tasks, including classification, segmentation, or object detection. And you can see the M flag works most effectively on those label-intensive tasks, such as segmentation and detection. For the classification, it also achieves very comparable performance against the other approaches at the time we submit our work. Okay. So let's talk about the second challenge, which is the misalignment. So recall in our previous work, what we do is simply do some MSE, trying to minimize the projected text embeddings to make it closer to the projected vision embeddings. But there are other more popular approaches, such as CLIP, okay, one of the work developed by OpenAI, which is one of the most popular framework for the vision and language contrastive learning for alignment. What they do is that they do not only consider the positive pairs, they also consider the negative pairs. We're trying to increase the discrimination power of this alignment, okay? So another nice thing about CLIP is that at the test time, you can do zero-shot classification. So basically, for example, if you have like a 10 class, you make as a text prompt and send it to this CLIP model, and it will calculate the similarities between this text prompt to the image embeddings. And the one with the highest similarity will be picked as the label. Okay, so this is the zero shot. And in their experiment, they found that using CLIP, the zero shot CLIP, it can achieve higher robustness on the images with natural image shifts. So on the y-axis, these are the performance on the out-of-domain datasets. On the x-axis is the intra-domain performance. As you can see, the purple is the CLIP's performance, which is much better than the ImageNet pre-trained models. But if you look at it closely at their technical details, you will find that one of the major attribution of their success might be they trained their data on much larger scale of the dataset. Okay, so which is around 400 million. So this is really the power of the data. But they also compare their method to other contrastive learning methods, and their method works the best at that time. Okay, so it's quite natural for us to think, why not just apply this to our medical domain? However, it didn't give us a very promising performance compared to MSE. So there is a very funny thing you can find that. So if you in the CLIPs, what they do is they simply treat that the images from different subjects, they are negative pairs. But in reality, in medical domain, even these images, they are coming from different subjects, they can express a similar pathology. So their reports are quite similar. So if you're doing this, you will introduce some ambiguity into the learning. So what we do is we're trying to propose some fine-grained alignment by disentangling the images into pathology and anatomy information. So you have like two streams in both the image modality as well as the text modalities, and you do the alignment at these two levels. And then you fuse this feature together to perform the downstream tasks. So I'm not sure if I have time to give this in much details, but the idea is give a text report, we apply some NLP technique called the named entity recognition, where we extract the triplets, which consists of the anatomy, pathology, and existing label. So if there is no, for example, there is no search funding, then the existing label will be 0, okay? And then we send it, or we generate a prompt based on these triplets. For the anatomy, we simply, is like similar to the CLIP, we just give a very simple prompt. For the pathology, what we do is we're trying to also exploit the external medical knowledge base, where we're trying to make a dictionary and trying to look at the dictionary and find its definition. So in this way, you give a rich information for the pathology you get from the medical report. Okay. So with these text embeddings in the anatomy and pathology, you can then send it into the training of the vision part and trying to get the vision stream to disentangle the anatomy from the pathology. And we propose 3 losses in this work. One is the existing loss, which basically when you send, for example, this will be like a attention module where you send a query about one particular anatomy and ask whether this anatomy presented in this image or not. Okay, so you got some representation and you send into a existence predictor. So this is simply a binary cross entropy loss. The second loss we introduced, we're trying to encourage the coexistence of the pathology as well as the anatomy inside of the same images. Okay, so this is also very similar. Different from CLIPS, here we also perform some contrastive learning, but we are doing this at a much low level, which we're trying to align the pathological text embeddings to the anatomical embeddings and treat all those non-existent pathologies as negative pairs. Okay. So here we do some prototype learning because in the medical image, there are multi-to-multi mappings, and that will increase lots of computational power. So what we do is we're trying to reduce it to just align the vision embeddings to the average of the existing pathologies as the positive pairs. Okay, this is simply a computational trick. So these are some results. We compare our method to lots of different method in this field, and we do it also evaluate in both the zero shot as well as this data efficient fine-tuning settings where our method achieves the best performance. Okay, so let's talk about the third challenge, which is the ambiguity as well as the complexity in the medical report. So this is particularly a work that I did in Oxford, where we're trying to align the text report to the ECG. And the problem we are tackling, if you attended the first day summer school, you may remember that first talk is talking about the survival risk prediction. So the problem setting is quite similar. Okay, so what we're trying to do is given a ECG image, which is cheaper and widely available, we're trying to predict the risk of getting heart failure in the future. So you can easily model it as a neural networks to predict its hazard, the risk score. The higher the risk score, the higher likely that it will get the heart failure in a very early stage. Okay. And if you look at this hazard, if you look at this loss function, we'll find that the loss is dominated by the existence of this data with heart failure in the training data set. So we use the UK biobank data to train this network. If we directly use it, we'll find the network will find it very challenging to converge. This is because the ratio of this heart failure, even in the real data set, is really scarce. One thing is because we are using the UK biobank data, which is over healthy population. Okay, so the ratio is really low. So it's natural for us to think whether we could first pre-train to using large-scale ECG as well as the medical report to pre-train it, and then we fine-tune it on the specific small cohorts. Okay. The problem in the ECG report, so in this work, we're using the PDB-XL, which is collected in German, but unfortunately, the report we found are written in 2 different languages. One is the German, another one is English. Okay, so there are some bilingual problems in these medical reports. The other problem is about the uncertainty. So most of this ECG report, if you look at it, because they are not a very high accurate testing, so clinicians prefer to using some very model or advert or some phrase to describe the probability. For example, using this is likely to be some disease or this is probably due to. So there are some uncertainty involved in this report. So can we directly using LLM to deal with the uncertainty? But in reality, we found that it's not working quite well. So what we do is we're trying to do some text pre-processing. by connecting to the clinical code. So each report, we extract them. This is very similar to our previous work. We were trying to extract the anatomy and pathology code. But in this work, we're trying to convert this raw ECG report into a set of SAP code. So each ECG, they can have different symptoms and different diseases. So you have multiple tuples here. And we use numbers here. So 100 means that this is very competent. 0 means that this is not likely to be. Okay. So once we got this SAP code, we can then send it to in our large language models, okay? And we can also resort to the medical knowledge data sets to construct medical prompts like this. And then we can send it into the large language model to get some embeddings and do some reweighting based on the confidence score. So this is very easy and intuitive to understand, right? So this is the kind of like a visualization about the representation we got from the LLM by doing this. So the red cross means the healthy subject, which is very close to the STT change, which is reasonable because some STT change can be happening even to healthy subjects. The green dots here are the myocardial infarction. So the healthy population is really far away from the myocardial infarction, which is also reasonable because myocardial infarction is a disease, okay? So by doing this, we can first align the ECG to these clinical reports, and then we fine-tune it on the downstream heart failure risk prediction. We compare our method to a sort of different pre-training tasks, including disease classification, which is this one, together with SR. SR means signal reconstruction. We also compare our method to raw text to ECG alignment, where you simply translate them into English and you send it to get some embeddings. And our method achieved the best performance, as you can see for the most for this one, which then is really trying to understand uncertainty inside of the medical report. It gives you a very unstable performance. On the hypertension cohort, the risk score is even lower than doing nothing. Okay, whereas our method can still give you some reasonable performance improvements. So this is very interesting. Okay. We also compare it to lots of like traditional methods. So clinicians will first derive some clinical biomarkers by extract some information, for example, the duration between 2 hour peaks as one of the indicator for the heart failure risk. And we collect 15 biomarkers that reported in the clinical literature, and we use it as put it into the simple risk prediction model. And on the left-hand side is the traditional way. On the right-hand side is the deep learning way, where we produced. You will find that our method performs better to stratify the low-risk groups from the high-risk groups. Okay. So to recap, so we have discussed some of our past works about how we leverage multi-view data, how we leverage multi-tap data, and applications cover from diagnosis, prognosis, as well as treatment planning. We're trying to predict the drug response. We found that it can improve the data efficiency as well as it can improve the accuracy on the downstream task or segmentation accuracy. So I'm going to talk about our last work, which is about how focusing on the health equity. Okay, this is kind of like application. So what we do is in this particular project, we're trying to answer whether we can achieve advanced diagnosis using low-cost modalities for a particular disease, which is pulmonary hypertension. So pulmonary hypertension is kind of like a life-threatening disease currently affecting 26 million people in the world. And to select the right treatment for pulmonary hypertension, gold standard is trying to do the right catheter catheterization, where you send like catheter into through your neck and trying to measure your pulmonary artery wedge pressure. So this is invasive, and this requires skilled clinicians to help them to measure the blood pressure. So one work we have done before is trying to using non-invasive modalities such as MRI to derive the pulmonary hypertension, the pulmonary wedge pressure. So in this work, we're trying to see whether we can utilize some low cost, because MRI still not every hospital can find an MRI scanner, even especially in low and middle income countries. Can we try to detect the pulmonary wedge pressure from local, such as X-ray or ECG? So in this work, we're trying to do some multimodal learning by jointly modeling into a joint distribution using the mixture, the product of experts, VAE, where each modality will be sent into a VAE, and the joint distribution will be modeled as the product of expert, because the first two VAEs are basically modeling, trying to regularize the latent space into a Gaussian, and the joint of them can be derived as a product of experts. So at the second stage, we can do some flexible fine-tuning by either using the X-ray, then we only focusing on the X-ray part of the latent representation from the VAE, or using the ECG part of the VAE, or we using the joint representation to fine-tune the model. So here's the result. So we first pre-train our model still using the MIMIC dataset, which is pre-trained on X-ray images as well as ECG images, which is 50K. And on the downstream task, we only have roughly less than 800 pair data. So we perform both unimodal fine-tuning as well as multimodal fine-tuning. So in 3 different scenarios, our method performed the best, and the highest performance is achieved by leveraging both modalities. Okay, so this is also some visualization to explain how it works. And I think Emma will also give a talk about the XAI in the second part of this afternoon. So here we're trying to just using the atomic attribution, which is similar to the gradient activation maps, and trying to highlight which part plays most important role when deciding whether this patient has a certain abnormal pulmonary wedge pressure or not. And in both cases, we found that for this is the abnormal cases, it will focus more on the right heart part of these images, which is consistent with the clinical findings. Okay. So you can also, so this talk, I think there is also kind of like a consistency between our work and the recent trends in this field, where you see at the early stage of the deep learning, what people do is trying to leverage image pre-trained, ImageNet pre-trained mode and fine-tune it to their task, and the overlap will be very small. So you didn't find a very substantial performance improvement on certain tasks, especially when the overlap is small. So with the recent development of self-supervised learning, which is my second solution, we're trying to leverage intra-domain data, but unlabeled data to do some self-supervised learning. So the overlap is high, and we can get a better performance. But the transferred knowledge is remain at the mid-level, because we're still doing some pixel level things, or we didn't do any domain knowledge injected into the, or to better get the pre-training part. So our recent work is focused on multimodal, and this is majority of the work we focus on how we leverage a clinical report, which consists of lots of clinical knowledge to help us to better get the representation. So we think this is kind of like a high-level transfer learning. Okay. So to summarize my talk today, so we talk about some the pitfalls of traditional AI pipeline to develop a medical, especially the medical image AI models. And we present a new recipe, which is currently one of the most popular paradigm in the medical domain, in medical imaging domain, where we're trying to first pre-train it or leverage existing foundation models, and then we fine-tune it. You can think that we first get a foundation model, and then we fine-tune it to make it as an expert in a particular task. We found that by exploiting multimodal data, even you have only single modality data, you can still, for example, in the image, you can have different views. You can still do some multimodal learning. It can help us to capture more comprehensive view of the data to improve the better performance on the downstream tasks, as well as robustness. And we also talk about how we leverage language reports, especially medical reports, as a free supervision to improve the better performance. We also talk about the challenges, existing challenges, as the misalignment, representation collapse problem, as well as ambiguity and complexity in the language. So we resort to 3 different approaches, including disentanglement, regularization, as well as how we inject medical knowledge into the alignment process. We also talk about its applications, not just focusing on only improving data efficiency or the accuracy from an engineering view, but also trying to do some interesting application that can improve the health equity. So what is the next? Okay, so this is very interesting. So last year, Ilya, which is the co-founder of the OpenAI, gave a talk at the NeuroIPS talking about like pre-training is going to be end. Okay, so I put it at the very end of my talk, otherwise it will ruin my talk. But interestingly, there are lots of people that don't agree with this view. So when people, which is the developer of the Gemini, talk about the pre-training is only over if you do not have any imaginations. And other people also backed him as saying that there are lots of data in the world. The only over is about the text data, but there are lots of imaging and vision data. So I think I hope with my talk, you can think about whether in your applications, you can explore multimodal data, trying to improve the representation learning. And the second direction I feel in this field is about trying to move it from data-centric or model-centric development into deployment-centric in the healthcare sector, especially trying to improve the adoptions in clinicians or increase the trustworthiness in the patients as well. And this requires a very comprehensive evaluations and how people can evaluate. And this is very important to provide some explainable insights about why the model failed. Okay, so traditional approach is just using XAI, which just I view this as a passive way to get some information. So including like using gradient activation maps. So just present with the user saying, okay, this is the focus map, and you can guess what's happening and see whether this is correct or not. The other thing I think is more interesting is about how we can using additional modalities such as language. So using human understandable language to explain what is happening. So can you tell me why you make this prediction, and can you tell me what's happening inside? So you can get more interactions between AI and the users. However, so this is one of the work we also recently accepted at the MICAI, which is focusing on this still like a medical proposed LLM called MET VLM R1, which is based on DeepSeek's recent technology in the GRPO. And we found it works quite good, even with just fine-tuning it from a large model, which is the equivalent 2B model to our medical data set, and it performs quite good. We also published the code, the pre-trained models on Hugging Face, so you can scan the code if you are interested and play around with it. However, the problem is still about the hallucination problem. This is something we also found in our work, that the produced text can sometimes be irrelevant to what presented to the model, or it can also give you some dummy words or non-sensational or even context inputs. So there is still a large room for improvement in order to achieve such kind of a vision to enable trustworthy AI in this field. So we encourage more researchers joining in the field of the multimodal AI. So this year in September, we organized a special session on the multimodal generative AI in healthcare in Cambridge, which is part of the International Conference on AI for Healthcare. So we currently have a deadline for the abstract, which is 5-page, and you can feel free to submit it before the end of June. So still, although less than a month, I think there's still some time. You can just submit some preliminary work in this special session. And we are also organizing a third workshop on multimodal AI in Barbican Centre, London, which is 2 weeks after our session in Cambridge, which will be more open to even preliminary work because it's just a place for networking and present your latest development in this field. And then you can still submit it to other venues because there is no proceeding. And nice thing about this, you can volunteer, and in that way, the registration fee will be waived. And there is also some hackathons and some prizes for the best poster presentations. So feel free to submit your early stage work if you feel it's not ready for publication, but it's also good for just networking and seeking for collaboration. Okay, so that's the end of my talk, and I'm happy to answer questions. Thank you.